Okay, so the main challenge at present industry is facing, if we have to tell it in key takeaway, is primarily we get engineers who are good breadth, or we get engineers with depth, but they don't have the breadth. So this, I mean, the current trend, and because of form factor reductions, and I mean, even in bigger engineering, the interference between one domain to another is becoming more and more predominant. For example, thermal versus EMI. EMI is electromagnetic interference, electromagnetic interference with antenna. So there, I mean, normally engineers, each of these type of engineers will come with their own set of guidelines, rules, or analysis, and say they want this. But the trade-off has to be done between different domains, and that is possible only if one can understand where the other person is coming from, and where how we can meet at the right point. I'm not using the word middle, because the trade-off you may make is not exactly at the center point. So given that, I'll this as a typical disclaimer. So Intel, whatever, I mean, you see, which is like a third party, we don't guarantee the data. We request you to go and look at the original source. And I think rest of it is basically Intel. I don't want to waste time given the limited time. So this is how I organized the agenda. So on the left side is the slide number, and this will be the topics we will be discussing. So if you look at, I mean, 15 to 20 years ago, when somebody walks out of the college, comes to industry, two things. There are, I mean, there is a gap observed by the student from what they learned versus what is done. It's not a mistake of either academia or the industry. The challenge with industry is they have to get it done, and they have, and the way industry used to work is they have a basic understanding, and they go logically and solve the problem. And most of it is intuitive. For example, if you have an op-amp design, you have to debug. You actually debug looking at how two pins of the op-amp is, I mean, behaving. So, I mean, I'm trying to take electronics as, because of my background, as example, but please feel free to question if is totally, I mean, new to your subject. So, I mean, if you look at this part, it's this, it's basically Maxwell's equation. The Maxwell equation, of course, is relevant for fluid dynamics as well as some background sound. Am I audible?
Yeah,
Hello.
Ajay, yes, you are audible. Yes. Yeah.
Okay.
Please proceed.
So this is, I mean, applicable both to electromagnetics and fluid mechanics. Some people are very averse to reading electromagnetics, and then when they come to engineering work, they have a set of ground rules which they follow. So this is how the gap existed between what is taught in the theory and what was done in the industry. So, and when you are in the industry, you don't refer to the typical textbooks at school. Some of these books were popular. Primarily, I mean, these books gives you a set of rules or set of caveats by which you can analyze the problem. So people will go and use one of these methods to fix the issues. Now, especially, I mean, for example, many of the analog circuits will have random oscillations. So if you look at Bob Pease, he has 2-3 chapters of which tells how to identify the source of the oscillation. Yes, that is the toughest point. If you can point out which is causing this issue, then you can go and fix. So, and we go there and then we fix. So that was the, I mean, type of books which we used to use, and still people use in cases. People have not come out from using thumb rules and ground rules. It may be applicable to probably certain set of engineering disciplines, but by and large, as we go more and more complex, much more thorough analysis is needed. Here is another example when you are making a system. The system can be might be used in different places, like in a building they can be used as energy management. In a industry, it may be used for automation, data monitoring, or I mean, there is, I mean, in the cockpit, avionics plays a very critical role. So they have multiple requirements, each of these applications. So these applications typically have some of those requirements, like you have to sense the state of the either sense the data which needs to be quantified, like in case of energy meters, you have to collect data and send it to the electricity board to actually give you the bill. And in case of probably in a field, you want to measure the position of a ball in a big factory. You may need a sensor which gives feedback on where your ball position is, or if you have to measure temperature, humidity, toxic gases, you may have to have typical sensor. So when the sensor comes, normally they are very low in signal value. You need analog front end to do the conditioning and give back give to the compute system so that they can process it. And when you are naturally, you need a processing unit to make many decisions, and to actually make all of these work, you have to have a power supplied to them, and and this has to be put in a proper mechanical structure so that I mean, many things. If it's a modular design, it should be stackable. If in case he has to go into a certain, for example, if it goes into aircraft, it has to withstand mechanical vibration and other things. So the ID should be in a position to, we use the mechanical case as ID. I mean, that's a terminology used inside Intel. The ID has to be done properly, and ID also has to protect. ID is not just a mechanical structure. They also have a structure which protects the equipment from many other things, electromagnetic interference, ESD, and all of those. So system engineer, typically what he does is he gives the spec to each and every engineer, a sensor design engineer. I mean, here I'm talking about a large scale application. Suppose you are doing a temperature control, everything can be done by one person. But in case of large systems, the system engineer will give the requirement to these individuals, and probably it's a best input output requirement, and they come back, deliver what is asked for, and it's just putting them together for the system engineer. But that scenario is changing because, for example, because of the very close proximity, your CPU logic may interfere with your analog, or your analog may not be up to speed. So you may have to use a different techniques to slice the data and then get the input. Your casing. Is there a comment or input?
No, it's fine.
Yes,
I also,
it's fine.
Okay. So the ID has its own restriction. For example, if you take a phone, people are driving more and more thinner one. I mean, from 8 mm, 10 mm thick phone to 4 mm laptop. I mean, phone is has a lot lesser components and functionality compared to a laptop, and you can see the Microsoft Surface Book, which is extremely thin, and the ID brings in those restrictions, and each and every aspects of engineering has to look at it and then come up with a solution. So the system engineering part is getting tougher, and he is something like earlier days, he cannot just give a requirement to others and assemble things. It has to be a well coordinated, coherent effort that needs to be done. So this briefly, I talked about if you look at SMPS or analog circuit designers, they resolve everything by using logic and then divide and conquer method. First thing is that is not working. So if you had to build something in a system, you need thorough analysis. And then that's where tools coming. Even if you have tools, simulation tools, you need much deeper understanding of the subject, because most of the tools use numerical computing method, and they are not perfect. I mean, they don't give. So you should be in a position to really figure out simulation data is junk or it's meaningful. And like we discussed in the earlier chapter, the breadth is required to understand the limitation of the next domain. And if you don't have, there are products which just failed. And in my experience, people who come from different domain with vertical knowledge alone, and when they sit together to design a complex product, lot of it is just rat holing in the meeting. I mean, each and every person make an assumption of what the other, the domain of other person, and they argue their point based on their assumptions. And to make things worse, if you take a Surface Book, they will have Shield, or Apple, they have the Shield, and they have the best of the design. Same thing if you go to Foxconn design, which they sell in India, they may not have a lot of these in place. People have pressure to show innovation. So what they do is they will go look at this low cost design and come and challenge the engineer that this is done in that design, why can't you do? I mean, but the challenge may be subtle. Sometimes you have to make 2% increase in performance. The trade-off you have to make may be large. So that is still, I think, still that problem exists in industry, and I think that's where academia has a major role in making them understand when they go to industry what is that they have to do, and what is the current state, what is that they have to do differently. And industry has to collaborate in this to make this successful, because industry knows what is the current challenges which we are facing. So if you this is just to show the engineering. I mean, we normally see probably 5 to 10 engineering discipline. Most of them is 5 at the undergrad level, but the specialization and domain expertise in once you go to industry is large. And the same mechanical engineer which comes out of college can take the role of mechanical designer, and or they can take the role of thermal engineer. They can take the role of a material engineer. So I mean, even though they have the common degree, the scale of expertise changes. So in this, the problem we are seeing is, if, for example, we hire a mechanical engineer and we want him to work on say 2D materials, the ramp up is a challenge. So if you're working at 2D material, you need to understand that things at the quantum physics level, right? And mechanical engineer to go there, it's a lot harder. So what they typically sought to do is they will try to use a simulation tool, and especially for 2D materials, in my experience, they go to a tool, multi-physics tool like COMSOL or others which CST and others have. The current problem in simulating 2D materials in any high-level simulation environment is not matured, and they give some results which will not show up in the lab. And one way of improving the accuracy of these simulation is you may have to write your own empirical relationship, which means that relationship has to come from atomic level analysis, which means you have to go to a tool like quantum base to do the analysis and compare and use that empirical formula in COMSOL. So, so that actually becomes tough because subject like quantum mechanics, people don't want to learn, and industry cannot teach them from basics. And I mean, the engineering goes in a different direction. So in my case, I was trying to use graphene in EMI shielding, and unfortunately, the simulation was not going well, and we had to do a lot of lab work, and it took 2.5 years to mature the design. And hardly, if simulation works, maybe 6 months to a year, we would mature. And if simulation works, we will have, we can use the same methodology for different things. I mean, I gave an example for electronics, and I think graphene has a very large scale of application. So, I mean, I've never seen this to happen, but this is just a concept. So if you really have a concrete building and you want to avoid heat coming into your building, probably a thin layer of graphene coating will absorb all the thermal energy and release them out in as like in plane energy, which for a civil engineer is very useful. But to get graphene to work, it's not so straightforward. There are multiple manufacturing methods. If you have to get a very good graphene, you have to go to a complex manufacturing method like CVD, which is slow and which is expensive. Some of these low end where you spray the graphene on the wall is not a purely a monolayer material. They have unevenness. They will not give you the expected thermal behavior. The same thing if you want to use graphene to increase your strength in a mechanical structure in the car or anything, you will face the same issues. Purity of graphene is one of the biggest barrier to break, and that's why this technology is so slow to be absorbed by the industry. So there are a set of technologies which may govern many things. I think many of you will be aware of this. So AI, surely it's going to dominate. They are getting matured day by day. Actually, they influence other things also. So IoT, naturally, you can have embedded sensor anywhere, any application, and then the, I mean, that has to, if works in conjunction with AI and big data, there will be wonders happening. And material itself is not something like you buy this gauge wire or this thickness steel. We do that is changing given the 2D material coming into place, and that's where on the previous slide I told the same graphene can be fine-tuned to different functionalities, and to do that, the main important thing is to get the simulation environment running. I mean, prototyping is cumbersome, also take time. Sometimes if you have to design a graphene from fine-tuning one functionality, it takes a month and a half to get the new sample, and if there is some error or deviation in the sample, you have to do again. So improving the simulation accuracy is very important, and this can come only from in-depth understanding of subjects like quantum physics. The same thing, I think the nanotechnologies sensing will almost influence everything, and the data they can I mean, they can go and sense in places where normal sensors cannot go, and that along with the artificial intelligence will take many things up to a different height. Quantum technology looks like they are in early stage, but claims are they will be ready in next five years. So the last one is more of an example where AI plus nano is expected to make a very big breakthrough, and this is actually happening a lot faster than we think. I mean, for example, if you have to use a magnetic nanoparticle to guide the nanoparticle with medicine to a certain cancer location, or you wanted to remove the plaque in the arteries of the heart, this can be done. I think the one major challenge they are struggling to overcome is the toxicity of the magnetic nanoparticle. If you find a way, this is doable, and this will still be expensive because I think I had that photo somewhere. Let me share. So if you have to guide a magnetic particle to a certain location in the body, you may have to have a very large magnetic structure, which precise magnetic field, which will move the particles to a specific location. So I think I'll discuss when I go to AI thing. So, but the same thing can be done at a much lower cost if you can use AI. And this probably might work at home itself, where if these sensors sense some of those pre-warning signals from on patients who are critically ill, and in today's world, many of the old people have to stay on their own. So this may actually reach out to the medical system and then get the help as soon as comes. So the other thing is, I think I see only very few data on this. The nanotechnology is expected to increase the lifespan by 5 times. So the very reason is, instead of going to you go to do a health check, you go to the hospital where the nanoparticles will actually go to the specific fat location. They can rotate at much higher speed and burn them instantaneously. So every year, whatever fat you eat, you can remove, or any other thing, cancer or any toxic material, which is, well, I don't know when this will happen, but this is one technology can be a game changer. So this is another example. Probably I'll go quick on this. I have worked in automotive. I mean, this has been there for some time. Probably, I think this is the this engineering probably is a leader for or pioneer in the need to understand each and every other domain. For example, this hybrid engine, if you are a microelectronics engineer, you can't just look at you cannot just do your logic circuit design, develop a software without understanding the harsh environment, whether it is thermal or EMI. Some of the time, the EMI needs to be addressed with the software. If you, I mean, that's the trend today. If you have to control electromagnetic interference or electromagnetic immunity, we can do many of the things in software, and software engineers should be in a position to appreciate, and the code they write has to happen in precise timing, in a very short timing. If earlier stages, when I tell the timing, software engineers will come and say it's absolutely not possible to code it within that time. So, but if the software engineer understands the limitation, they may actually come with very innovative idea of recovering the system from electromagnetic interference. So your power steering or active steering control, transmission, a person who does these need to understand, even a mechanical person need to understand how the power is transmitted when to the engine, and what is the inertial level in the gearing, inertia in the dynamic system. When you want to control, how do you make that happen without toppling? So the larger dynamics you should know, and then I mean the time, the response time, the time within which you have to respond. So each one of those engineers should be in a position to understand. So for example, I've given this table. So these are the verticals a mechanical engineer should know, but he should equally understand the software, chemical, electronics, electrical, because detonating is, knocking is something completely unavoidable, but how to manage them without damaging the engines is critical. And he has to work with the chemical engineer to make sure that they make a trade-off. So the same thing here. I mean, there's nothing. So in case of electrical engineer, he has to understand, because automotive is a very harsh environment. To make things worse, even though there is a EMC standard, the car, each and every car company will have their own definition, a spec of EMC, which will be sometimes be 10 times the standards. So they have to be experts they have to be expert in their field, and they have to have a knowledge to a level where they can understand the limitation of other domains. So this is a case example which I had worked. I was one of the pioneer in working for power door application. I don't know whether in India we have any cars with power door. One thing is the power door has limitation of space, and also you have to open the door. Power door essentially we all have passive entry now. Passive entry, when you put the hand, the locks open. But power door is something you put your hand, the door automatically opens, and then while getting in, you touch, the door closes, which typically in the car, many people don't realize they have done half lock. If you look at the lock knob in the door, they have two states. The first lock, which is the half, and then the second lock is one which completely locks. And when you close the door, it may stay in the first lock. People won't realize, and that's where these power door applications will make sure that they close the door properly. All you have to do is just a touch. So when we were working in this design, the biggest challenges we had is we can't use a big motor. So one, due to space, another due to the energy, because when you are walking to the car from somewhere else, the power drained should be very, very little, because when this happens multiple times, the motor will drain your battery. So that actually defines your battery. So that means the gear is something not driven like continuously. The way, because you also need a lot of power to move the door. So one way they do it is they pulse. They give a very high voltage to the motor, which will have enough torque to push. And when you do that, you can't do that for a long time, because the motor will eventually heat and get damaged. Then on the off time should give them the time to heal, and that's how it's done. So in this case, for example, the software engineer need to understand how this is managed, right? So you have how this healing works. Otherwise, if somebody wants to give a code by getting a spec, that has never worked. In fact, in this project, we started like that, and then we had to move out those software engineers and bring in engineers with a mechanical and electrical domain background. And another thing is classical problem is this. gears can go into resonance mode. When that happens, actually all these gears will be totally, powdered. They come out as powder. So one has to really understand the resonance. So the resonance in the system is not just by the gears alone, it's the driving mechanism, it's the how you transition from peak power to low power. All of those has to be looked at. But one thing is, I recently looked at certain cars. I don't know whether it is there in India. You can, by gestures, you can open the door. So when you're walking to the car, you do a gesture, the power door automatically opens, you sit and just touch the door and it automatically closes. So, so in this, all these electrical, electronics, thermal, software, mechanical, even manufacturing, reliability, all has to work coherently and understand the limitations of each other domain. So I took another example where challenges come. See, when you have multiple domain, there can be interference from, or cross domain interference from one to another. So in case of electronic systems, as a CAD engineer faces the biggest challenge, because he has to, for him, the board, the board he designs has very high level of density. The number of lines he has to route every day, the package, number of pins and packages are growing. How he can route this from A to B itself is a big challenge. Over and above that, the other domain people will bring in their own restriction. For example, signal integrity may ask a PCIe or USB line to have more spacing so they can reduce crosstalk and maintain the bit error rate. And a power integrity person will ask for a very low DC resistance to the CPU. And a shield person. See, when you have a very high density board, each and every of the board is very critical. And when a EMI engineer asks for a shield, there are multiple ways you can do the shield. And the trade-off is many. The shielding effectiveness, the EMC engineer should trade off his shielding effectiveness to manufacturability and what the layout is. The density of the boards around the electronics. So there are different types of shield you can make. If a particular design demands rework in service, then the shield has to be in a position. You should be in a position to remove the shield and put the shield back. And the major challenge between this is a heat sink, where the major challenge between heat sink and the shield is normally heat sink does not. It's not practical to do the shielding, grounding of the heat sink in the way EMI engineer wants. For example, EMI engineers' typical standard requirement is up to 6 gigahertz. So you may want to ground each and every 2 mm. So you can see this structure of the heat sink, and it's practically not possible to ground them at every 2 mm. So how he makes the trade-off? So he has to look at his energy source, it does the energy source at gigahertz, 6 gigahertz series enough to emit? Do they need 60 dB attenuation at that frequency, or if 5 dB is okay? So there is a lot of interaction has to happen, and each of them should understand each of others domain. Same case, the power people want more area because they want to reduce the resistance. So they want to take as much area as possible. So if you take up a lot of area for the power plane, again, the real estate for others will come down. So this people has to make a trade-off. And one of the critical things is inductance of the power plane. The inductance of the power plane drives how much good quality power we can deliver to the IC. So ideally, if you want to rate the inductance between positive and negative line, they should be positive layer and negative layer, ground layer should be next to each other. So that makes difficult for signal engineers, because sometimes they will land up with ground on one side and power on other side. That's that we call it as dual referencing, which makes it life very, very difficult for a SI engineer. So this is a forward-looking thought. As I told, so there are a lot of AI plus nano is surely going to take our healthcare in a different level. It can do lab. You can do analysis of a medical condition much better. It can focus to a specific area. In many cases, you don't need a invasive procedure, and some of these, I think, still still from what I know, probably if somebody knows better, they can correct me. The indicator for a colon cancer or a prostate cancer is through blood test, but this appears only at a late stage. So you have to do either endoscopy for the colon cancer with period of, each doctor tells different numbers, because my father had a colon cancer. So different numbers on the frequencies. So the best way would be to use nanoparticle, which can sense any metastate at the earlier stage and then report. So in sensing, they will make a very big change, and also in surgeries, giving localized treatment for cancer, especially where the chemo medicine doesn't have to go through a lot of, it doesn't have to affect the rest of the body. So we did some research work with IIT Guwahati in using magnetic nanoparticle to do the fat burning, both to the specific fat location burning. We couldn't do throughout the end, but the biggest challenge we faced is the particle flow analysis. The many multi-physics tools support them, but even if you use them, it's a lot of effort. You have to understand how the blood circulation happen, and at what levels. It's not just a 2D flow, right? It's a 3D flow. You have to figure out, given the complex nature of human body, we have to figure out where, how to trace a particle. Even if you want to use magnetics to maneuver the particle, you should know how to maneuver the particle. So that is the work we did. And so I think this is I've already discussed. So not only between different domain, one very challenging, one very important challenge I face is you have different engineers do different things. In a big company, we don't have the luxury of people doing everything, every aspects of these engineering. One is because of the number of projects. Second, the scale of analysis. We may do huge number of DOEs, like 3,000, 4,000 cases to ensure that the quality is very good, and also the yield is good. Even if yield is off by 1 or 2%, it's a huge disadvantage for companies like Intel. So there is signal integrity. All these are basically electromagnetics. We have signal integrity engineers, power delivery engineers, EMI antenna engineers. Primarily, the way today they work is they use the tool to get the data and then try to manage different things to achieve the solution. And a engineer who comes from college without a deeper understanding of electromagnetics, they don't see this all are electromagnetics problem. Probably this is one-dimensional, this is two-dimensional, EMI is three-dimensional. Antenna is also three-dimensional but narrow band. So they don't look at this, and they actually, you will see people fighting. The power delivery engineer will fight for more area, or they will say for high speed, I would you just do dual referencing, which is positive on one side and negative on the other side. So, given the level of shrinking we are doing, people have to look holistically and then see how you can come across. And this is actually one area where academia will be helpful. They actually educate them where they will apply, and these things are basically same, but we use different abstraction and analysis technique to solve that particular problem. Probably, industry can give us the cases where they had struggled with this, and then how we can converge. So this is something actually it's a nanoscale challenges which we have started to look at. So we are trying to do some using graphene. We are trying to solve some problems which at present I'm not in a position to disclose. So here again, the heat is rufo non-transport, and in a 2D material, fair amount of even conduction, electric conduction is also at phonon transport. And naturally, you don't have free electrons like metal. You have to use the Dirac fermion concept. So both of the actually from the analysis point of view is same. And we have earlier worked with Professor Chen in MIT. In fact, his work does not classify this as two different things. He calls it energy flow in nanoscale materials.
Ajay,
Actually, I wanted to put, yeah.
I am sorry about interrupting. Can we have some time for questions? In
Yeah,
fact, I
yeah,
have
sorry,
already
I don't
Yeah,
posted.
know.
yeah.
Yeah, yeah, yeah.
If we can
Even
have some
please.
Okay.
questions because
Yeah, yeah,
it's
yeah.
been
Yeah, I'm
over
done.
soon.
Yeah, yeah.
Yeah,
Oh, thank you.
Thank you. Thank
Well,
you. So the
thanks.
first
no
question
problem.
is from me, Ivan. Okay.
Yeah, I think someone would like to ask. It's about maybe you can share your thoughts on curriculum design. So, if we use undergraduate students in electronics and communication engineering, so what do you think maybe we can do? Do we need to change it, or maybe we need to make some adjustments, or maybe it actually works fine? If you can share this, your thoughts. That was a question from Professor Selvan.
Okay, so uh, I mean, at present, the challenge I see is people see electromagnetics is something about electronics and magnetics, and it is they look at. I mean, they don't even get a context of how they apply, and if we can make a balance to share some of these and examples and how the analysis is done is one way of making them aware that they are really applying it to the field. And industry can help by exposing them either in terms of internship or 1-2 weeks industrial exposure in some of these application will help them appreciate I mean, where it is applied. It's not something, a set of equation in the book. So that would really help.
Yeah. Thank you. Thank you, Ajay. Thank you.
Thanks, Ajay.
Did I answer you?
I think you probably
Did I?
answered Professor Selvan's
Yeah, yeah.
question.
Yes, yes. Yeah.
Okay.
Are there any more questions? Probably we maybe spend like 5 minutes for questions. I know it's a little bit over time. If you have any questions, you can just write them down in the chat or just ask directly. While you're thinking, I just want to ask you a question, Ajay, if you don't mind. So
Sure.
you talk about, this collaboration between different types of engineering, right? Electronical, mechanical, software engineering. So this is very important, right? So,
Yes.
and because I was thinking about how we teach our students, and well, kind of probably like similar questions to Professor Selvan's question. So, do you think we should learn them more, like not only like one discipline, like let's say mechanical engineering? So, um, should we teach them maybe like also electronical things, and that will take maybe extra, maybe 1 year, or we can just sort of like try to do something with the current program, and I don't know, have some kind of like major industry related projects that they can work on and things like that. So probably like still keep it within 4 years, because here like at Griffith we have like 4 years undergraduate degree. Or do you think it's kind of maybe we need to teach them a little bit longer for extra extra time? So what are your thoughts
So
on
I
this?
think extra longer or 1 more year, I think people will get discouraged.
That's true,
Many
yes.
people whom I see who go for the doctor's degree don't prefer to go for this specific reason. The at least one semester, one subject which categorically shows how each of these are critical in getting things done, in getting in a product, maybe product design can be one course which could be mandatory, and where we expose people to these different aspects of engineering, which they need to understand. And another thing is the curriculum should engage in a way that at college level, people, learning is always done by the individual. Teaching only facilitates at college level. So they have to clearly understand that, and when they come to industry, or when you do the product design course, they, beyond a point, they should have that ability to learn by themselves. That's the one of the biggest challenge I face. If you ask someone to, even the math paper they have done, and if people do excellent job in college in doing the math, but when they come to industry and when we ask them to go back and work on that, a lot of people are very hesitant. I don't know whether I answered your question.
No, that's a good answer. Can I just ask you then maybe one more question if I don't see any question in the chat? So this is just like for your experience in India, right? So when you see new graduates from school, right? And they maybe like come and like work with you, are they already work ready? So can they do like many things, or still like you have to teach them certain things that they didn't learn in the uni? So what is your experience? Because we have like something similar here in Australia. So sometimes, you know, like when we talk to the industry people, they say, well, maybe you should focus on this more or that more. And sometimes in the industry, they actually like teach them different things that we don't teach them. For example, here at Griffith. Do you have a similar experience in Intel India when people come and work to you just right from a uni? And like, are they like really very good, like very experienced, or they still like know like maybe lots of theory, but maybe they don't have much practical experience? So just would like to...
Yeah, it's a classical problem. They are not ready to do the work. The way, I mean, even postgraduates from the so-called tier 1 in colleges have this problem. The way we handle is we ask them to do execution. When I say execution, so you have a problem, you have to simulate. We teach them the steps of how to simulate, and we give them problems from the projects and ask them to simulate. And they do that for 1 or 2 years. In that process, they learn what they have to do next.
Okay.
Even for PhD students, right? If the domain is slightly away, they need time. I mean, they are not ready to do on day one.
Well, thanks for answering this question. And I think we're already out of time, so I would like to conclude the session. Thanks again, Ajay Kumar, for your time and for this interesting presentation, because you talk about industry perspective, something sometimes we miss it because we talk about how to teach, but also we want to see this connection with the industry, like why we teach and what are the needs. And well, thanks for sharing your experience and your thoughts about this collaboration between different disciplines. Thanks for your time, and thanks a lot. And want to also thank Professor Sevan for arranging this presentation, and all the people who attended this presentation. Thanks for your time, and hopefully it was very useful to each of you.
Thank you, Ajay,
thanks for this nice opportunity. So I hope things will pan out. So any help or anything needed, you can feel free to reach me. Intel has their collaboration program. we can see how things work out if you want to change in curriculum. Thank you,
Sure.
Selvam and Derifit.
Yeah. Thank you, Ajay. Bye.
Thank you.
Yeah, thank you, everybody. Have a nice day, and see you next month. Yeah, bye, everybody.
Bye. Yeah, bye.